Welcome back to Chapter 1.4, the Law of Large Numbers and the Central Limit Theorem, Part 9 of 10. In Part 8, we saw fat tails poison Devon's average by violating the no single contribution dominates clause. Now we make the danger precise. There is a hierarchy of bad behavior, and you must learn to locate your data on it, because has a mean is not the same as the theorem bites quickly. This is the distinction Devon needs, and it is subtle enough to deserve its own paragraph. A distribution can have a perfectly well-defined mean mu and still have a gigantic or even infinite variance. The mean and the variance are separate integrals. The first can converge while the second blows up. The tail probabilities are what decide it. How much weight sits far out in the tail determines whether the variance integral converges at all. So when you ask whether the central limit theorem applies, the question is not merely does this distribution have a mean, it is does it have a finite variance, and that is a strictly harder bar to clear. A family of distributions that makes this concrete is the student's T, with new degrees of freedom, which finance routinely uses as a stand-in for fat-tailed returns. For nu greater than 2, say nu equals 5, a common fit for daily equity returns. The variance is finite, so the central limit theorem does eventually hold, but slowly. The tails are heavy enough that you might need n in the hundreds or low thousands, not 30, before the standardized mean looks normal. For nu equals 2, the mean still exists, but the variance is infinite. The theorem's hypothesis is violated outright. There is no sigma to standardize by, and the standardized mean histogram never settles onto the bell. So even within one family, a single parameter slides you from a slow theorem to no theorem at all. For nu equals 1, the Cauchy distribution, the canonical horror story, even the mean fails to exist. The integral that should define mu does not converge. The sample mean of n Cauchy draws has the same distribution as a single draw. Averaging 1,000,000 is no more informative than looking at one. The law of large numbers itself fails. So having a mean buys you, at most, the hope that the law of large numbers works. It does not buy you a fast central limit theorem, and if the variance is infinite, it does not buy you the theorem at all. Devon's crypto returns live in the heavy but finite variance zone, closer to a low nu student's T than to a normal. So his sample mean is eventually consistent and asymptotically normal, but eventually might require far more data than he has, and any confidence interval he builds from a few hundred observations is built on sand. To summarize Part 9, there is a hierarchy of bad behavior, and you locate your data on it by the tail probabilities, because the mean and the variance are separate integrals. With a student's T at nu above 2, the variance is finite and the central limit theorem holds but slowly, possibly needing thousands of observations. At nu equals 2, the variance is infinite and there is no sigma to standardize by, so the theorem fails outright. At nu equals 1, the Cauchy, even the mean fails to exist and the law of large numbers itself collapses. Averaging 1,000,000 draws is no better than 1. Having a mean buys only the hope that the law of large numbers works. It does not guarantee a usable theorem. In Part 10, we watched the bell refuse to form and asked what Devon should actually do.